Hello, my name is Victor, and in the previous video we learned about the first 20 elements of the periodic table. Remember, there are other elements down here. There are other elements as you go down here. Now in this video we want to learn about trends, trends down the group and across the period of this periodic table. We want to learn about atomic. Let me write here so that we have a checklist. We want to check atomic size or atomic radius. We also want to see reactivity. We also want to see melting and boiling point. We also want to see electrical conductivity. We want to see this 4 points. If there is another one, we are going to add it as we move forward. Now, talking of atomic radius or atomic size, what is it? We drew in your books or in your class, you must have drawn something like this about the structure of an atom, and you are told this is the nucleus where you have protons and you have neutrons. Then you have the various electrons arranged in the various energy levels. And you must have also learned that these energy levels, the first energy level, can accommodate a maximum of 2 electrons. It can have 1, but it can accommodate a maximum of 2. When you have more than 2 electrons, you also have an added energy level where electrons arrange themselves. They can be 3, they can be 4, they can be 6, they can be 8, but they cannot be more than 8. So when you have more than 10 electrons, because for 10 you have 2 and then 8. However, if you have 11, you must add another energy level. So the first energy level accommodates a maximum of 2. The second accommodates a maximum of 8. And the third accommodates a maximum of 8. For the first 20 elements, you might not need the fourth, because automatically for calcium it will have only 2. However, look at it this way: you have a maximum of 2, a maximum of 8, a maximum of 8. In the comment section, answer for me what is the maximum number of electrons that can be there in the 4th and the 5th energy level. Now, it is present in KJCR books, so you look at it. Now, when we are talking about atomic radius, we talk of hydrogen. Hydrogen, the atom will be like this. Force of hydrogen is that. Then you come for lithium, it has how many electrons? 1, 2, 3. We can actually use the green number, that is atomic number. The number of protons is equal to the number of electrons. So this is lithium. So this is hydrogen, and then we have lithium. Then you can go to sodium, which will have 2. Then have 8. Then we can go to potassium. Oh, sorry, it will also have 1. Then go to potassium, which will be because it has how many electrons? 19. This one, if you are to write electron arrangement, you would write 1. This one is 2, 1. This one is 2, 8, 1. This one would be 2, 8, 8, 1. So we are, this is the number of electrons. 2 plus 8 plus 8 plus 1 will give you 19. And this is 19. This is 11. If you add this, it will give you 11. This one, if you add, is 3, and this one is 1. So when we are talking about atomic radius, what are we talking about? Atomic size, we are looking at this. The distance from the center. The distance from the center. The distance from the center. So what happens? It is increasing. So as you go down the group, you can write in your notes that you have increasing atomic radius. Increasing atomic radius. Sometimes when the question comes for application, you will not be asked to draw this. You'll be asked, compare the atomic radius of sodium and potassium, or an element that is written maybe Z and here X. Compare. You will say the element K, potassium, has a larger atomic radius than N. Why? Because it has an extra energy level. What we have realized is that we are just adding one energy level. So energy levels here is 1, these are 2, these are 3, these are 4. And you can also get them from here. 1, 1, 2, 1, 2, 3, 1, 2, 3, 4. So this one has a larger atomic size. This applies for all, even for metals. So this one in brackets, you can write for both metals and non-metals. Atomic radius or size increases down the group. Increases down the group. If you are given elements that are not indicated by their actual symbols, you will talk about element X has a larger atomic radius than element Z. Sometimes this one is especially for high school. You have that question, or senior school. Now let us look at another relationship. So we have finished. We have done this atomic radius of elements. Now let's talk of the reactivity. Let us talk of reactivity. How then do these elements compare when it comes to reactivity? Is this potassium more reactive than sodium, sodium more reactive than lithium, or the other way around, that lithium is more reactive than potassium? How do they compare? Now, in your reactivity series, you must have learned somewhere that the reactivity series starts with potassium, sodium, you have calcium, you have magnesium, and you have some other elements that are not among the first 20 elements, the kinds of lead, zinc, and zinc and lead. Then you have hydrogen, copper, and you go down, the least reactive element is gold. The least reactive element is gold. Anyway, I was writing this just to help you compare these two, and probably also these two. That calcium appears higher in the reactivity series than magnesium, and also potassium is more reactive than all, especially more reactive than sodium. Now, I do not want us to use this, I just wanted to demonstrate. Don't use this as the explanation. That potassium, ukiulizwa, or when you asked, is potassium more reactive than sodium, you say yes, it appears higher in the reactivity series. No, don't use that explanation. Now, I want us to compare this and this. How do they react? How do metals react? Metals react by losing an electron. So, we want to take away this electron for these two. So the most reactive metal is the one that it is more easily to grab or to take away that electron. The ease of taking this electron, which one is more likely or easily has greater ease of losing this electron. Now, these electrons, as we had said, I don't know whether, yeah, in the other video, is that they are held together by attraction of nuclear charge, or nuclear attraction from the positively charged protons. So positively charged protons attract negatively charged electrons. The protons are present in the nucleus, the electrons are around. Now, the longer the distance from the nucleus, the longer the distance, the least the amount of charge reaches the outermost energy level. Let me rephrase this in a more local language, Swahili. Now, ile nguvu iko hapa ya protons ndio inashikilia the electrons. Kama hapa ni mbali, hii distance ni kubwa sana. Sasa itakuwa ni ngumu. Itakuwa na iko mbali sana. Hii haipati nguvu nyingi from the nucleus, na hii iko karibu. When you compare this one is longer while this one is closer, as we have said about the atomic radius. So this one with a longer distance will receive least charge, so therefore it is easily lost, while this one receives stronger charge compared to this, therefore it is not easily lost. However, when you are comparing these two, you talk about again the distance. This one is further from the nucleus, receives lesser charge than this, lesser nuclear charge or nuclear attraction. Therefore, it is more easily lost. So, what have we said? When you are going down, this is more reactive than this because it has a larger radius and therefore easily loses the outermost electron, the electron on the outermost energy level. So as you go down the group, you are increasing reactivity in brackets for metals. This is for metals. We have talked about atomic radius and we said it is for both. As you go down, the radius is increasing for both. Now, as you go down the group, you are increasing atomic radius and you are also increasing reactivity for metals. However, now let us compare this. How will reactivity for nonmetals behave? Remember in group 8, it has complete octet. Particularly this one, they have a stable element where the electronic arrangement, so for neon, electronic arrangement for neon is 2, 8. For argon, electronic arrangement is 2, 8, 8. So this one, the outermost energy level is full. So therefore it does not easily lose, does not lose or gain. So it does not react. They are non-reactive. Now that they are unreactive, we are going to compare for group 7. So we are going to talk about group 7 and we will have two. We will have chlorine and fluorine. Fluorine has the electronic arrangement, of 2, 7, while chlorine has the electronic arrangement of 2, 8, 7, because it has the atomic number 17. So when you are drawing, you will draw like this. Okay, let me draw it more clearly so that you don't get confused. So this one, fluorine, has this, has 1, 2, 3, 4, 5, 6, 7. While this has 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. So we have this fluorine has a smaller radius compared to chlorine. This one is smaller, while this is larger. Now, how do metals react? We said for an element to react, it needs to have either 8 here, or either to have a 2 like this one, just 2, and does not have any other element. So, excuse me, apart from hydrogen and helium that could react and have a stable electronic configuration of 2, and also lithium and beryllium and boron, these are metals. The rest will always want to gain or lose to make sure it has an 8. Let me also iterate on potassium. Potassium had this electronic configuration. So here we want to make it 8. It is easier to lose 1 than to bring 7. It is easier to lose 1 than to bring 7. That is why this potassium will always lose. However, for this, it is easier to gain 1 than to lose 7. So this one will react by adding an electron. This one too will react by adding an electron, and the new electronic configuration will be 2, 8, 8. And this one will be 2, 8. The new electronic configuration. So we want to see which one has greater ease. If there is only one electron around here, and both want that electron, which one will take it faster? When you have a larger atomic radius, the nuclear charge is the one still attracting the incoming electron, and also for this. So, therefore, when you have a smaller radius, it is easier to gain that electron. It is easier when you have a smaller atomic radius. It is easier to gain an electron than when you have a larger radius. When you have a larger radius, it is not easy to gain that electron. Therefore, this one, if you draw the reactivity for nanometals, we are talking about this, or all this area, these are nanometals. You could add this one. So we write this. This is more reactive than this. So the arrow is opposite of this. This one faced down, while this one will face up, increasing reactivity for nanometals. Yes, so this is very simple. The relationship between reactivity for metals and nanometals revolves around the atomic size, the number of energy levels. And again, you need to understand whether that atom reacts by gaining or losing an electron. And let me also add something here so that we understand about metals and nanometals. Metals will lose electron. So the first 3 groups are generally considered to have metallic properties. For example, we have aluminium. Aluminium will have the electronic arrangement of 2, 8, 3. So it is easier to lose 3 than to bring in 5. Let's talk about carbon. Carbon has the electronic arrangement 2, 4. So it either gains 4 or loses 4. So therefore, it has both properties of metals and nanometals, but mostly behave as a nanometal. So generally, these 3 groups have metallic properties. Hydrogen can neither gain or lose. Hydrogen has just 1. It either needs 1 brought in, or you just remove that one and it remains just without any electron. So there is a question that can be asked: hydrogen can be placed here or here, because when it is here, it behaves like halogens. These are halogens that react by gaining 1 electron. Now these two, this group 2, react by losing 2 electrons. For example, magnesium will be written as the electronic arrangement 282. It will lose 2. All these lose 2. Calcium will have 2, 8, 8, 2. it will lose these 2. So this lose 2, this ones lose 3. Aluminium, it is 2, 8, 3. It will lose 3 electrons. So we are going to learn more about the charge, and probably you already know about that, but what is quite a little bit challenging is about understanding the electronic arrangement, atomic size, and reactivity down the group. So these ones react by gaining electrons, and therefore the smaller the radius, the greater the ease of reacting. So increasing reactivity as you go up the group. You can write that in your notes. Now let us expound. We'll do another video on melting point and electrical conductivity. The video is becoming long already. It is 20 minutes. Now we can expound a little bit, just a little bit, on the atomic radius and reactivity across the period. Atomic radius and reactivity across the period. Now we talk about period 3. Period 3. When you are talking about atomic radius. Now what we had noted is that when you are going down the group, the number of energy levels determine the atomic size. Now, when we are going across the period, we have the same number of electrons, and therefore, not really electrons, then the same number of periods. So for this one, they have 3 energy levels. So for sodium, you have sodium, you have 1, 2, I'm not drawing this to scale, and then you have 1. So then you can compare with aluminium. Aluminium, which will have 1, 2, and here you have 3. Or you can distribute them well and say 1 there and 1 here. So again, I insist, I've not drawn this to scale. Don't come and measure this distance. However, I want you to note that you have the different number of electrons. You have 2, 8, 3. This one is 2, 8, 1. So the only difference is here, and also another difference is in the protons here. So number of protons are that 11. Electrons are 11. Protons here are 13. Electrons here are also 13. So what do you think? If you compare these two, will they have different or the same atomic size? Yeah, atomic size. Will they be the same? If your answer is the same, but if your answer is different, yes, we are there. Now, the answer is that the two will have different atomic size. However, which one has a larger atomic size? We kind of want to talk about the nuclear charge here. We want to talk about the nuclear charge. As you go across the period, you are adding the number of protons. The energy, the nuclear charge that attracts the electrons towards the center. The pull will be stronger, and therefore this outermost energy level, as you add more protons, gets closer to the nucleus. Therefore you continue reducing the size. Hello? So as you go across the period, from here up to the nanometers, just across, you reduce. This one has decreasing atomic radius. This is period 3. So we kind of choose period 3 to study because it might differ slightly in others, but the general trend is that as you go across the period, you continue reducing the atomic size. When you are asked to explain how or why, you would talk about the increasing nuclear charge, the number explained by the number of protons that attract the electrons towards the center. If you need summarized notes on this and how to answer directly, I'm going to provide my number. Okay, already it's present in this channel. You can ask for the notes from me. I have around 3 pages of summarized notes on how to explain. However, just how I'm explaining in this video, it would help you to understand. But I'm sure you would want to know how then you would summarize or state in an exam. However, now you know the trend: decreasing atomic radius. Talk of increasing nuclear charge as you go across the period from left to right, from this left hand to the left hand side. Alright, how then does this affect this one, there are several other factors that would affect. However, let's talk about reactivity across the period. Yes, we could still use this too. So here you have this is sodium with 2, 8, 1, and this one 2, 8, 3. So we said for metals, so we have answered atomic radius across the period. What about reactivity? Reactivity for metals, we are talking about losing this and losing this. Remember, reactivity requires energy, and we talk about ionization, energy. The energy required to remove an electron for metals from a metal atom. So you want to remove this one electron, or you want to remove the 3. So for each electron, to remove each electron, you require some energy. So it is easier or requires less energy to remove 1 electron than to remove 3. And it also requires less energy to remove 1 than to remove 2 for the case of magnesium. So in other words, we are saying group 1 elements are more reactive than group 2 elements if you compare in the same period. So this one is more reactive than this. Sorry. Sodium is more reactive than magnesium. Magnesium is more reactive than aluminium. And in that sense, sodium is more reactive than aluminium, or is more reactive than, we are talking about metals here. So if you are asked, you would explain about the number of electrons required or to be removed. So here for metals, you draw this arrow and you say increasing reactivity for metals. Increasing reactivity for metals. What about for nanometals? Let's compare chlorine and sulfur. So chlorine or sulfur, we will draw sulfur as 2 . So it has this one, no, this does not have this. This is sulfur. And the electronic arrangement is 2, 8, 6. Then you have chlorine. Chlorine has 17 electrons. 17 electrons. Good. And the electronic arrangement is 2, 8, 7. 2, 8, 7. So you need to add 2. You need to bring 2 here. And this one, you need to bring only 1. You need to bring 1 electron. So again, we have said, as we have said about losing electron, also for gaining electrons, you need energy to bring that 1 electron. So for this case, you need 1 you need some energy to bring this electron or to bring these two. So is it again easier to bring one or to bring two? We used to take this example of, suppose you have a need and a student has come to class, does not have a pen. You provide them. It is easier to give them a pen than when they come to class they don't have a pen and they don't have a book. They don't have two things. Sometimes you would feel like, hey, this person is too dependent on you. So it is easier to give or to gain that one electron than to gain two. And it also applies here. This one requires 3. It is a little bit difficult to gain 3 electrons. So just similarly, like this, we said it is easier to lose 1 than to lose 2. It is easier to lose 2 than 3 when you're comparing this, and we said this. So we are, in other words, we are saying this chlorine is more reactive than sulfur. This only requires 1 electron. This one requires 2 electrons to be stable. Phosphorus requires 3 electrons to be stable. Therefore, remember, these are not reactive. I hope you noted that. Inert, do not react, do not react. So this arrow, you write increasing reactivity for non-metals. Increasing reactivity for nanometals. So now let us recap on the different trends that we have drawn in this video. I had promised to go ahead with this in this video, however we are going to do it in a separate video and upload it right here. Now, we talked about the atomic size. We said atomic size or radius increases down the group for all. If you compare boron and aluminium, aluminium has a larger atomic radius than boron. Oxygen and sulfur, sulfur has a larger atomic size than oxygen. And the same, argon has a larger atomic size than neon, right? So what about reactivity? We said metals and nanometals have different trends when it comes to reactivity. We said this one with a larger atomic radius has greater ease of losing its outermost electron than sodium. Therefore, reactivity increases as you go down the group. The same here. Calcium is more reactive than magnesium. And aluminum is more reactive than boron. We came to the nanometals, we said group 8 does not react. These are inert gases. We said we could talk about group 7, halogens, group 6, or group 5. So then, remember in between these two groups there is transitional elements that have more than one oxidation state. So if you have learned with drawing that transition elements, don't worry about this. There is some gap, but in terms of groups, these are the groups. Now, when you are comparing this, we say if this has a larger atomic radius than, if chlorine has a larger atomic radius than fluorine, chlorine larger than fluorine, then to gain an electron we need that small atom. It will be easy to bring it that electron because the outermost, the incoming electron is receiving stronger charge from the nucleus because of the smaller atomic radius. Yes, we talked about this and we said increasing reactivity, this one is more reactive than this. Alright, then we talked about across the period. We said across the period, we said that atomic radius decreases as you go from left to right of the periodic table, because as you go from the left side to the right side of the periodic table of the period, the same period, you are increasing or adding nuclear charge. Yet the number of energy levels remain constant. The other thing we talked about is reactivity across the period. We said the number of electrons required or to be lost or to be gained for that reaction to happen. And we took period 3 again. We said this one loses 1 electron, this loses 2, this one loses 3. So if you are comparing aluminum, magnesium and sodium, you would say reactivity increases as you go to the left. And that's why we drew this. Or if you want to say about from left to right, you would say it decreases. For metals, be specific. However, when you come for nanometals, you are comparing these 3. We say this one requires only 1 electron. Pretty easy to react. Requires 2 electrons. Who will give them 2? Requires 3 to react. It becomes more difficult. So as you go to the right, reactivity becomes more easy, and therefore this one has greater ease of reaction. Now, with this, I want you to draw one lesson that in this reactivity increases this way, and also reactivity increases this way. Therefore, where do they meet? This one is the most reactive metal in this periodic table. Remember, you have the periodic table does not get this is not the limit, it is longer. So as you go down this period, the lowest in this group is the most reactive. So if they bring the periodic table with Z here and ask, there's a question that had RB, and they asked which is the most reactive metal. Many students gave potassium. This was the most reactive metal. That's something I wanted you to note. What about for nanometals? Reactivity increases this way and also increases this way. So as you go this way and up, where do you meet? This one is not reactive. So we are talking about this group, the highest and the farthest. The highest up the group and the farthest to the right, which is this one. So you can note the most reactive nanometal is fluorine. There is no higher. Like this case we have said, there could be others there are definitely others that are more reactive. But this one is the most reactive nanometal. If a question asks, which is the most reactive nanometal? Fluorine, and you have it. You have learned something today. Very good. Now, we will meet in another video as I explain melting and boiling point and about electrical conductivity for metals and how they relate in this periodic table. Be sure to catch that video. Please, the best gift and favor you can do to this creator, this teacher, is to subscribe. Please subscribe to this channel, and I will sure be able to consistently upload more content for you to revise in mathematics, chemistry, and other science subjects. Thank you. See you.